Continuing the discussion on Ks, we have this equilibrium of 2N2O5 goes to 4NO2 and O2, and recognize that these are all gases. So take a moment and see if you can write the Kp and then the Kc expression for both of these, for this reaction, I'm sorry. So here's the Kc and here's the Kp for that reaction. So I'm going to derive, there is a relationship between these two, so I'm going to derive that equation to kind of show you where it comes from. So remember back to gas laws. Our favorite gas law is, of course, PV equals nRT. Well, if I take PV equals nRT and I manipulate it, I could get pressure is equal to N over V times RT. So N over V is obviously moles over liters. That's concentration. That's actually what we have in our brackets. So what I could do is I could take this expression of the Kp and I could plug in the concentration values and multiply it by RT. So that's what you're going to see next in my notes here. Okay. So what I have is NO2 times RT to the power of 4, the whole thing, O2 and then N2O5. Well, if I just look specifically at the concentrations, okay, so if I circle essentially the concentrations, okay, that's essentially my Kc, okay. Then what do I have left is the RT. So this is going to be multiplied by RT, but what is the power going to be? Well, I have 4 times 1 on the top, so that's essentially 4 plus 1 is 5. And then you're going to subtract what is on the bottom, so that's going to give me a power of 3 for the RT. So generically, it is Kp is equal to Kc times RT to the power of delta N. So what's delta N? That's going to be products, number of moles of products, minus reactants. So again, how much product did I have for gases here? I have 5. And then what do I have for reactants? That's 2. So that's where I get the 3 from. Okay. Now the R we're going to use for this is 0.0821 liter atmosphere mole Kelvin. And do realize this will change depending upon your units. But for right now, we're going to assume everything's in atmospheres. I will give you specific information if it's not in atmospheres. Again, that's the one drawback of Kp is you don't really have a unit to hold on to. So there are 2 problems here. What is the value of Kp if here's the Kc? And then repeat for this reaction if the Kc is at that. What would be the Kp? So I'm going to pause the video and then show you the answers. So for the first problem here, you took the Kc, you multiply it by R, and then remember your temperature needs to be in Kelvin, so hopefully you didn't make that mistake. I have 2 moles on the product side minus the reactant, which is 1, so that's brought to the power 1, so you should end up with 2.72. The second equation has the same number of moles on both sides. I have 2 moles of gas over here, 2 moles of gas here, so the Kp is equal to the Kc. Okay. All right, some finer points about K. So go to the next page. So what happens if you reverse or multiply an equation? What happens to the actual K? So I've given you this equation, and this is the K for this particular equation, the way it is written. So the one thing you must understand going forward is anytime we're looking at an equilibrium reaction, since it can be reversible, we always say on the left is the reactants, on the right is the products. Otherwise, you're going to start into a big circle and you're not going to be able to tell which direction you're going. So if I reverse the reaction, so what I did was the products became the reactants, and this is now the product from the reactant. So what happens to my K? Well, remember, K is going to be products over reactants. So essentially what you're doing when you reverse it is you're going to take the inverse of the K. Okay, so mathematically, I'm going to take the inverse of 2.5 times 10 to the negative 4. So it comes out to be about 4,000 for that K value, for that reversed reaction. Well, what happens if I multiplied everything by 2? So again, you're just going to change the stoichiometry. Well, what's going to happen to the K? Well, realize the K is going to be that factor above it, because essentially what you're doing is this is going to be squared, this is going to be to the power of 1, and this is going to be squared as well. So you're going to be squaring that K. So you're going to take 2.5 times 10 to the negative 4th, and you're going to square that number. And you get about 6.25 times 10 to the negative 8th for your K value. So whatever you do to your equation is going to be what you bring it to the power. If you reverse it, you reverse the K. Also having to do with K values is what happens if you add reactions. So this is an example of a diprotic acid. And we're going to be talking about acids a lot in the next couple chapters. But what I taught you in first semester is this is a diprotic acid, meaning it has 2 H's to give off. When it gives off an H, it gives it off once at a time. So this first H comes off and you produce HC2O4 minus, and then that H comes off in the second reaction. So when you add them all up, you end up with the final reaction. But what is the K that we're talking about here? So the K for this one, these are both going to be called KAs. The first one is going to be called KA1, and the second one is going to be called KA2, because what we're talking about is the first hydrogen to come off versus the second hydrogen to come off. So let's write the expression. All I'm doing is putting my brackets around my products and then putting the reactant underneath. Same thing for this. And it doesn't matter the order you put things, by the way. So in my final reaction, I have H plus squared, right? C2O4 2 minus over H2C2O4. That's what my overall K is going to be for this reaction. Well, can you tell what you did to the Ks? So my Ka for this first reaction is 3.8 times 10 to the negative 2nd. The second one is 5 times 10 to the negative 5th. Okay. So when you look at the two expressions and you end up with H plus squared, okay, what are you doing to these Kas? Okay. So if you multiply them, you will actually cancel out the HC2O4 minus, and you'll be left with essentially what you need in your final. So what you will always do with Ks if you are adding is you're going to multiply them. So Ka times Ka is going to give you your final K. So in this case, it is 3.8 times 10 to the negative 2 times 5 times 10 to the negative 5th. So that's going to end up being 1.9 times 10 to the negative 6. So Ka1, Ka2. So you're always going to multiply the Ks if you are adding the reactions. Okay. You're always going to multiply the Ks if you're adding the reactions. So in the same idea of Ks, okay, what does the size of the K tell you about the reaction? So I want you to focus on the arrows that I have here, okay? So this Kp value is 1.4 times 10 to the 83rd. Recognize that that's a very large number, okay? So if you look at the actual arrows that I put on here, the arrow is pointing more towards the right than coming back from the left. So when your K is that large, it signifies the forward reactions pretty much goes to completion, okay? If you have a very small K, like this one is 10 to the negative 21st, that means it's staying pretty much as a reactant. So you might see an arrow pointing in this direction for that reason.